Okay, so finishing up this problem here, we need to find the critical values. So we set the derivative equal to 0 for these optimizations. We don't want the D and E ones. And we end up with this cubic polynomial right here. Now, that seems like it's going to be very, very hard to solve without a calculator because it doesn't factor anything like that. So much like when we have inverse functions and we're trying to figure out the clue, if it's a non-calculated question and it's not something you can algebraically solve, the solution is going to end up being relatively easy. So you kind of actually do guess and check. So can anyone think of a number between 0 and 3 that when you plug in for x makes that a true statement? 1, yeah. 1 minus 3 is -2, and -2 plus 2 is 0. So this gives you x equals 1. Now, if it were a calculator question, it might be an ugly decimal. In that case, you'd graph the left side in y1, graph that in y2, and then look for the point of intersection, and then store it. But x equals 1. When you plug in a 1, you get 0. So that's the critical value. So now, if we want to figure out what point is closest, we actually can use the EVT. We could say, okay, let's figure out what is the distance at the left endpoint, 0, what is the distance at the right endpoint, 3, and what is the distance at our critical value of 1. All right, now there's two ways to figure out the distance at 0. You can just come back over here and say, when we're on the parabola there, it's horizontal, it's 3 units. We know that's 3. But we can also, remember, plug it into our distance formula. Here is the distance formula that's in terms of x. So what do you get when you plug in a 0 there? You get 9 plus 0 is 9. The square root of 9 is 3. So you get the same answer. Same thing here. If you want to figure out the distance at 3, well, geometrically, that's straight up. It's just the y value there. You know it's 9. But again, if you weren't sure, you could just plug it into here, and you'll get the same value. Now, for the distance when x equals 1, we do need to use this. So let's see what we get. When we plug a 1 in, we get -2 squared is 4. And then 4 plus 1 is 5. We get the square root of 5. And by the EVT then, since our function is continuous on that closed interval from 0 to 3, one of those is going to be the maximum distance on that interval, and one of them is going to be the minimum distance not only on that interval, but everywhere. So which of those is the smallest? That's what we want. Square root of 5, yeah. So we could say, since if we had to justify, since d of x, or just d, well, what's the function? Yeah, d, we'll call it d of x, is continuous on our closed interval from 0 to 3, comma, by the EVT, the minimum distance is square root of 5 at the point 1, comma, and then we can plug it into the function, which is x squared, 1. All right, so ultimately it asks for the point on the curve. And so we did, we found it, 1, 1, and we gave a little bit of a bonus piece of information there. We gave the actual distance, the square root of 5. So that would be somewhere right in here, 1.1. All right, so notice that the endpoint ultimately was not the optimal value, but it was still relevant and easily could have been. For instance, if you look at this situation, this would be like a totally different type of problem. Let's say you had a parabola that opened at the vertex, and it opened really, really wide, And we had a point that was right here on the outside. What point on that parabola would be closest to it? Yeah, in this case, you could probably make a visual argument that it's the origin and not something that's further away, right? And so if you came up with an interval there, it would be horizontal wherever it intersects. That would be your one point, and then straight down would be the other, and then maybe at an interior point. In this case, it would be the end point. So just keep in mind as we move forward, whenever you're trying to minimize distance or find closest to a curve, that is the type of problem where the endpoints are possible winners. It's not always going to be at a critical value. Okay, because if you remember what I told you, without justifying 99 times out of 99 and a half or 99 times out of 100, the single critical value that you find on the interior is the optimal value you're looking for. This would be kind of the one exception when you're trying to minimize distance. All right, so we'll finish the rest of the optimization after tomorrow's test. I'm thinking that your test question for optimization is probably going to be a fence building question. Would you prefer that up to like example 1 where it's just a generic number question? Yeah. Let's build a fence, right? That sounds kind of fun. We'll get our construction juices going tomorrow. So, all right, we'll stop right there.